Hello everyone, nice to have you back. Today we're going to learn about this thing called goal programming. If you've been following the sequence of lectures in my Excel models playlist, which is the regular progression that I teach students, up to this point, all of the optimization models that we wrote together and solved together had constraints of a type that I'm going to refer to as hard constraints. And by hard constraint, I mean a constraint that must be obeyed or satisfied by a solution to your model. There are, however, situations in real life where you want to enforce a constraint, but you are willing to be a little flexible about it. That is to say, for example, let's say I have a budget constraint, and I initially tell someone I can only spend $1,000, but if you come back to me with a very nice solution that spends $1,000 plus $10, I probably would not be too upset about it, and if the solution was good, I might be willing to accept it. So there are situations where you would want to have this flexibility, and instead of saying I absolutely cannot go over $1,000, I say I would like to be within the $1,000, but if you deviate from that number by not too much, I'm still okay with that solution. And this is what goal programming is all about. And today I'm going to show you how to transform a constraint from being hard into a flexible constraint, or if you want to call it a soft constraint, by using a little trick in the algebra of when you write the mathematical expression for the constraint. It's a quite simple trick, but it's kind of ingenious, I think. Let's do this via an example, as always. Here's the story for us to go over. There's this guy who owns a hotel in Myrtle Beach, South Carolina, and he's thinking about expanding the facilities. And the expansion consists of adding additional conference rooms to the hotel. And these conference rooms, according to this table, can be of three sizes: small, medium, large. Here, the table gives you the square footage of each size of the room and how much it would cost to add a room of that size to the hotel. This person's initial goals are the following. They would like to have 5 extra small rooms, 10 extra medium rooms, and 15 extra large rooms. And he wants the expansion in total to be 25,000 square feet, and the budget he has for this is $1 million. Now we're going to assume that all of these are flexible requirements. This is ideally the person would like to achieve all of these goals, but if it is necessary to deviate from them, as long as it's not too much, the person would be fine with that kind of answer. So how do we write this down in a way that it's flexible? So the first thing I want to do with you is, let's say if these had to be satisfied, these requirements, exactly, how would we write down the mathematical model? We'll do that first, and then I'll show you how to transform that into a flexible model. So let's begin here. In this case, what would be the variables for us? Well, the things that we are looking for is, what should the expansion consist of? That is, how many rooms of each size should we have? So we can have 3 variables. We call it x1, x2, x3, or let me call them S, M, and L to represent. S is how many small rooms we're going to add to the hotel. M is how many medium. L is how many large rooms. So again, let's first write this down as if we were going to satisfy these requirements exactly. Let me go to a little pad here. So they say 5 small rooms. So if I wanted to do that exactly, I would write a constraint that says S equals 5, right? And 10 medium, so I would write M equals 10. And 15 large, right? Let me just double check. 5, 10, 15. Right. Now, if I wrote this, notice that there is no choice for any of these three variables. They're basically saying you have to be equal to 5, 10, or 15. But that's not really what I want, right? I want to allow, let's focus on the small rooms. I want to allow the S variable to fluctuate. If it wants to be 4, it can. If it wants to be 6, it can. But the way this is written right now, it's not going to allow me to do that. So I need to, of course, change this formula to something else. And this something else is what will allow the value of S, M, and L to fluctuate up or down. So the idea is this. I'm going to add some room here between the variables and the equal signs so that I can add more stuff. And here's the idea. If, let's say, if S wants to be less than 5, for this formula to work, I would have to add, right, something to the value of S, because S is smaller than 5. And if S wants to be greater than 5, for this formula to work, I would have to subtract something from the value of S. So we realize that if S wants to be different from 5, I'm either going to have to add something to the value of S, in case S is too small, or I have to subtract something from the value of S, in case S is too large. But because a priori I don't know whether S wants to be smaller than 5 or greater than 5, I need to allow for both possibilities to happen. So what I'm going to add to this formula is two terms. A term that will take care of the fact that if S wants to be too large, I need to subtract something from it. And if S wants to be too small, I need to add something to it. And I'm calling this O to stand for overage. And I'm calling this U to stand for the opposite of overage, underage. Again, that is to say, if S wants to be larger than 5, there's going to be an overage. By how much are U greater than 5? I subtract that how much from S, and that brings me back to 5. If S wants to be less than 5, there is an underage, that is, by how much are U, variable S, less than 5? And that how much is what I have to add to S to bring S, the value, back to 5. And because I don't know what situation I will be in, I need to have both of these possibilities in the formula. So let me give you an example. If S wants to be 3, to show you that this formula always has a solution, if S wants to be 3, I would have no overage and an underage of 2, and that comes back to 5. So if S wants to be 3, O would be 0 and U would be 2. If S wants to be 6, O would be 1 and U would be 0. So for whatever value you want to give to S, you can always find a value for O and a value for U that make the formula work. And this O and U essentially capture the distance between what S is and what S is supposed to be. We can call the value on the side either the goal or the target. And the value of S is what I'm going to call the actual. So was the actual result equal to the target? If so, both overage and underage are equal to 0. If the actual result was different from the target, the overage and underage will capture the distance, right? How far are you from where you're supposed to be? And that's the whole trick the main concept that allows you to transform any constraint from hard to soft, right? So now once you understand this idea, we can simply apply this to all of the other constraints in the problem. So M, right? The same thing could happen to the medium rooms. If it's too large, there will be an overage. Oops, let me go back to black here. If it's too large, there will be an overage. And if it's too small, oh, I made the pen thickness too much. If it's too small, there will be an underage, right? But notice, I can't call these two overage, underage again OU because they're not the same amount, right? There's an overage and an underage for the small rooms and another overage and underage for the medium rooms. So let me, for example, I could number these. This is, let's say this O1, U1, right? The over-under of the first constraint. The O2, U2, the over-under of the second constraint, and I can just proceed now like that. Okay, so now I am allowing SML to differ from 5, 10, and 15, and I will be capturing the difference in these variables OU. What else do we have in the problem? We have two more constraints. We need a space requirement, right? They would like 25,000 square feet. Let's do that. So the sizes are 400, 750, and 1050. So to calculate the size of the expansion, right, every small room would add 400 square feet to the expansion, so 400 times however many small rooms. Every medium room would add 750, and every large room would add 1050. Now this is the actual footage. Actual footage added. There could be an overage and there could be an underage, and the desired amount is 25,000. Notice when I am implementing soft constraints, the symbol will always be an equality, because that's what makes the over-under trick work. We're going to see later, is it true that it's always bad to be both under and over? That is not necessarily the case, but for now, I just want to emphasize you should always use an equality sign. And then later on, you can come back and see, well, does it matter if I go over? Does it matter if I go under? And if so, you can deal with that later. But to make it simple, always add an O and a U and make it an equal sign. And that works for every problem. The last constraint is going to be our cost, right? Let me see here if I can just slide this a little bit so that I can see. Okay, 18,000 for every small room. And then 33,000 for every medium, and 45,150 for every large. There could be an overage, there could be an underage, and the budget is 1 million. Okay, great. Now, notice that we started with the constraints and we did not do an objective for this problem yet. But if you think about it, you realize what the objective is supposed to be. If I have stated my desires, right, and what would be an ideal solution? Well, ideally, I would like all O's and U's to be 0, because that would mean that the actuals, the things that actually took place, exactly matched my desires. However, in this problem, if you make S equal to 5, M equal to 10, and L equal to 15, and you plug those values in here or here, you will see that you're not going to match the target numbers on the other side. Okay? That is to say, it is impossible in this case to fulfill what this person wants. And this is a very common thing in real life problems. That is, people ask you for things without really understanding that they are impossible. And that happens for a variety of reasons, mainly lack of complete understanding of the situation. And to be fair, the situation could be so complex that you can't really put all of those details together in your head and deduce that the solution you would wish for isn't really doable. But tools like this, models like this, allow us to figure that out and realize, you know what, you need to compromise somewhere. Great. So if I would like to have my over-under as small as possible, there comes my objective. I simply want to minimize the O's and the U's, because that will look for a solution that brings my actuals as close as possible to my targets or goals. So let's write that objective over here at the top. Minimize, right, the over-under of the small room, the over-under of the medium, over-under of large, and then the over-under of the area, right? And the over-under of the budget. Great. Oh, wait, is this showing here? Yes. All right. Now, this looks like it would work, but there is a little problem here. In fact, it's a couple of problems. Well, if you think about what the SML variables are, they're the room counts, right? Which means the O and U of SML are room counts. How many rooms are you under over? The O and U of the area are in area, in square feet. And the O and U of the budget are in money. So if I just leave this expression the way it is, I am adding together, rooms plus square footage plus money, which is not acceptable, right? The units have to match in an expression like this. So that's not okay. The other problem is an issue of magnitude. So imagine the following solution. I make all OUs equal to 0, except, let's say, the O of the small room that I make equal to 1. That is, I go over by 1 room. Well, the objective value of the solution is 1 because all OUs are 0 except O1, which is equal to 1. And imagine another solution in which I make all OUs 0, but I go over budget by $1, right? The value of that solution is also equal to 1 because O5 is equal to 1 and everybody else is 0. Now I have two solutions whose objective is equal to 1, which means in terms of the objective number per se, they are equivalent. But think about what these solutions are doing. Which one would bother you more? Going over the budget by $1 while everything else is perfect, or going over the small room count by 1 room while everything else is perfect? Well, clearly, if you're willing to spend $1 million, and if I come to you with a great solution that spends $1,001, you don't really care, right? But going over by 1 room is way more significant. So ideally, what you want to look at is not just the OUs in the objective in absolute terms, but in relative terms, as in percentage, right? By how much am I deviating from my goal in percentage terms? And that would kind of equalize all these deviations or normalize them to a comparable value, in addition to getting rid of the issue of the units, which we can't really add square footage to money, etc. So What I want to do is transform this objective into a percent deviation objective, right? By what percentage are you deviating from, and I'm dividing the OUs by the target, right? To indicate this calculation, O1 plus U1 over 5 will tell me I am deviating from the small room target by what percentage. So I divide each OU by the corresponding target. That transforms this objective into a percentage deviation instead of an absolute deviation from target number. So this both deals with the problem of the units and the problem of the different magnitudes of the target. So this is a much nicer thing to look at. All right, 2 more comments and then we'll do the Excel model. First comment, is it always that case that both O and U are bad? Well, not necessarily. In this case, for example, I think it's reasonable to assume that going over or under the room counts, these are both bad things. I would like to stay with those numbers. But what about the budget, right? If I find a good solution that is under budget, most likely this person would not complain. There are situations where if you're given a budget, you don't want to be under budget because maybe next time they're going to offer you money, they're going to say, well, you didn't use all the money the previous time I gave you money, so I'm going to give you less money this time. But let's ignore that case for now. In this particular case, let's say this is the person's their own money, so they want to, ideally spend less if possible. Now, by leaving the U variable in the objective, I am essentially asking solver, try to make U5 small. But if there is a nice solution with a large U5, I like that solution because it means it's really a lot over budget. So if a deviation is beneficial, you should not put it in the objective because the objective is trying to minimize a deviation. And you only want to minimize things that are bad, things that hurt you. So we could assume here that being under budget is beneficial. So ideally, what you need to do is actually remove U5 from the objective. Don't even put it there. Don't ask the solver to make it small. Second and final comment before the Excel model, it is also possible to prioritize these deviations or give them weights. For example, in speaking with this person, they could say, you know what, to me, meeting the total area target, the 25,000, is twice as important as anything else. If they said something like this to you, you could simply go in the objective and put a number 2 in front of those deviations, and this basically will tell solver to try twice as hard to make those guys small than the others. So we can do weights, and you can remove deviations that are helping you from the objective because you don't want to make them small. So this is our goal programming model. Let's go to Excel and I'll show you how to implement all of this, and then we'll see what the solution looks like. So here we go. I have here all the data. I have the SML variables in this position here. And in these 2 cells, I'm going to calculate, right, as we wrote in the model, the square footage formula, actual square footage, and actual expense. So row 8 will be all my actuals. Row 9 will be all my O variables, my overage variables. And row 10 will be all my U variables, the underage variables. And if you notice, the pattern of every one of these soft constraints is actual amount minus overage plus underage equal target or goal, right? Actual minus overage plus underage equal target. Actual minus overage plus underage equal target. So this is the pattern. So that part, the actual minus over plus under, I am going to put in row 11. And inside solver, I will say row 11 has to equal row 13, which is where the targets are. Right? So let's do that. Let's first calculate the actual square footage. Is just a sum product between the SML and their corresponding square footage, right? To get the expression we wrote down. And to get the costs, it's a similar expression, the SML times their corresponding costs. So now we have all the actuals, because the actual of the small room is just a variable S itself. There's no formula, right? Here, actual minus overage plus underage, right? Imitating what we wrote down in the math. And this is a formula I can copy to the right because it's the same for every one of the goals. Okay, so again here, actual minus overage plus underage. Great. If you recall from our objective formula, we were dividing, right, each OU by the target. So what I'm going to do in Excel to make this more flexible is the following. I'm going to create these expressions. I'm going to break them into pieces. I'm going to create the O1 over 5 in one cell, and in a separate cell the U1 over 5, and then the O2 over 10 in one cell, and another cell this guy, right? And then I have all these fractions that I can add together later. Another reason for doing this is that maybe you would like to, not necessarily as I did here, this 2 is the same weight for both O and U, but maybe you want to put a weight, give this guy a different weight from the other guy, right? So I will create these fractions separately, so because if you want to weigh them differently, you can, right? Great. So let's go back here. So in row 16, I'm going to make all the O's, the overages, divided by their targets. And in row 17, all the U's divided by the target. So I could do, so this overage divided by the target, right? And I can copy this over. This way I get all O's by target. And here I can do the underage over target, right? And copy this over. All right, so this gives me the percent deviations. And let's say initially we have a similar weight for all of them, so weight of 1. So everything is equally important. So to get the final expression, I can do a sum product between the percentage deviations and their weights. And now, because all weights are currently 1, this is simply equivalent to just summing up all the percentage deviations. But in doing it this way, it allows you to come back later and change one of these weights, and you'll see why, one reason why you want to do that once you see the answer. One final thing, remember that we spoke about dropping the under budget deviation from the objective because under budget is helpful. One simple way to do that, or eliminate anything you don't want from the objective, is just to make its weight equal to 0. So I can go here for the weight of the underage of the budget constraint, right? And make that 0. And that is like deleting U5 from the objective. Great, so we're ready to solve now. Let's do that. Solver, okay. And here we go. The objective is right here, B23. It's minimized because we're minimizing bad things. The variables, I can't do the whole block because it's not just a plain rectangle, so I can do it this way. The SML, select them. On Windows, you could type a comma now and then select all the OU variables. On the Mac, you can do this by holding down Command and then select all the OU variables. So in whatever way you do this, just make sure that in your changing cell area, you have 2 things capturing all of the cells that are painted gray here. In whichever way you want to do it. You could do this block here, followed by this block here, many different ways. Great. Constraint-wise, we're going to say first that the all the actual minus over plus under need to equal the target numbers. So row 11 equals row 13, right? And one more thing, which is, well, these are rooms, SML, they have to be integer. I don't want a fractional room, right? So we can select SML here, make them integer, and that will be it for constraints. Just remember to make variables non-negative, because the O and U have to be non-negative, otherwise the little trick doesn't work. And because this is all linear, simplex LP, and because we have integer variables, make sure to double check, come in here and check that this ignore integer constraints box isn't checked and the optimality percentage is 0, because we want the true optimal solution. Click OK, and now we can solve this. So let's see. Okay, let's take a look at what happened. The proposal here is the following. We are gonna get you, Mr. Davis, the guy who's asking for this solution, your 5, 10, 15 rooms that you wanted. So no deviation here. See, the OU of the SML is 0, 0, 0. This, however, will not perfectly match the other two requirements. Notice he wanted 25,000 square feet. We went over by 250, which, not too bad. And the budget was $1 million, and we went over budget by $97,000. So at this point, two things can happen. We come to Davis, we're the consultants, and say, here's a solution. Isn't it great? Davis may look at this and say, I'm rich, going over 97,000, that's okay, great job. And everything is fine, and you're done. Or this guy could come back to you and say, well, I didn't want to go over by that much money. Can you find me another solution, right? At this point, there's something you can do. You can say, well, I basically want to tell solver to try to drive this number here down a little, with more intensity. Likely at the expense of something else. This is the famous something's gotta give. If you want the 97,000 overage to go down, it is likely that some other, goal of your problem will suffer. Let's try. For example, I could change this weight from 1 to a 2 and solve again. Let's see what happens. As you can see now, we reduced the overage, right? Which is what we wanted. But there have been consequences. Now there is an underage in the area of 800 square feet, and I am under the large room count by 1. Let's say this guy still thinks this is too high, and then you get, mad at him and say, I'm just going to put 10 weight on the budget. And you solve again. And now, maybe Davis will be really happy because we're only over budget by a little under $7,000. However, right, we're under large rooms by 2, and we're under the area by 1850. At which point, Davis may be happy or not. If he's unhappy with something else, you can change the weight of that thing. And there's going to be a little bit of this back and forth until you converge to something. So notice, in a Go programming problem, the concept of what is an optimal solution has become subjective, because it is in the head of the person who is interested in solving the problem what a good trade-off is. And that's totally fine. This is still a useful tool for you to sit with that person and help them understand how the something's gotta give, trade-offs look like. If you want more of this, this is where you lose. If you want more of that, that's where you lose. And after doing this for a while, the person will eventually, come to terms with what pulls what down or up, and then you can converge to something that is satisfactory. Okay, that's the whole point of goal programming and building tools like this, is to give you more information for you to make a good decision. All right, this is pretty much the key parts of goal programming that I wanted to touch upon with you. I hope this video has been helpful, and as always, thank you guys for watching, and I hope to see you back here for more videos. Bye bye.